Welcome to EDU World Space.
Okay, so we have a question on gravitation, which asks us to calculate the force between an astronaut and then the Earth. Now, we are told in this question that the astronaut is 75 kilograms in mass. He's 75 kilograms in mass. Okay, all right. And then he is 600 kilometers above the surface of the Earth. Okay, he's 600 kilometers above the surface of the Earth. So let's say the distance between the astronaut and then the surface of the Earth is 600 kilometers. All right. Okay, good. Now, Sir Isaac Newton said that all objects are attracted towards each other by some amount of force. And now this force that he is talking about, that the force is proportional to the product of the masses, okay? The product of the masses between the two objects that we are considering. So in our situation, the astronaut and the Earth are two masses. And then divided by the separation between them squared, okay? R, give out, which is squared. Okay. All right. Now, what you need to know is that this distance R is the distance between the centers of the mass of the two bodies, okay? Between the centers of the mass of the two bodies. All right. Now, the Earth itself has a radius, okay? The radius of the Earth usually is given as, let me say, R is R subscript A, okay? It's given as 6,371 kilometers. Now that is the radius of the Earth, okay? Now, from Sir Isaac Newton, since he said that the distance, okay, the distance between the masses is between their centers, what it means is that in this R equation, we are going to remodify it and say that the force is equal to the mass m1 times the mass m2, okay, divided by the sum of the distance between the astronaut and then, let's say, r1 plus r A. Okay, so in this situation, my R subscript 1 or R1 is the distance between the astronaut and then the surface of the Earth. And then my R subscript A is the radius of the Earth. Now remember, this radius is squared from the equation. Always remember that, okay? It's squared from the equation. Now, the G that we see in this equation is we call it the universal gravitational constant, okay? We call it the universal gravitational constant, which is G. And G is usually given as 6.674, okay? 6.674 times 10 to the power negative 11, okay? Times 10 to the power negative 11. All right. And then the unit is Newton meter squared. Newton meter squared per kilogram squared. Okay, Newton meter squared per kilogram squared. All right. And then the mass of the Earth, okay, let's say M1, the mass of the Earth, M1, is given as 5.98 times 10 to the power 24, okay, 10 to the power 24. And remember, since it's mass, the unit is what? In kilograms. That's the standard unit or the SI unit we should be working with. Good. All right. Now, let's move on and look at the distances between them. Now, initially we said our R1 is 600 kilometers, okay? Our R1 is 600 kilometers, okay? Now remember, the kilometers must be changed to meters, okay? And then we have our RA, our subscript A, which is the radius of the Earth, giving us what, 6,371 kilometers, okay? Kilometers, and they are all in kilometers. So straight away, when we add these two, this should give us 971 kilometers, okay? 971 kilometers. Now let's go to our equation and now put in all the values that we have had or we have stated initially. All right, so we say F, which is the gravitational force, is equal to, we know that our G is 6.674, okay, times 10 to the power negative 11. All right. Now, times the mass of the Earth, 5.98. 5.98 times 10 to the power 24. Let us not forget. 10 to the power 24 times the mass of the astronaut, okay, which is 75. All right. Now, all this divided by the total distance between them, okay, and remember the total distance that we had between them, the total distance that we had between them is 971 kilometers. Remember, I said the kilometers must be changed to meters. So in changing to meters, kilo means 10 to the power 3. Okay, so make sure you include that. Now, all this squared. Good. So when you calculate, that should give you about 615. Yeah, 615 thereabout newtons. Okay, 615 newtons. All right, so this is what you get. This is the magnitude of the force, which is the force, the attractive force between the astronaut and then the Earth. All right, now what if the astronaut is on the surface of the Earth? How can we evaluate the magnitude of the force? Now, from our equation, we realize that the separation between the masses is inversely related to the force of attraction between them. So if the distance between them increases, the force reduces. And if the distance between them decreases, the force increases. So in this situation, when the astronaut is on the surface of the Earth, what it means is that the separation between them reduces. And so we should be looking out for the force of attraction between the astronaut and then the Earth to be greater than 615 newtons. Now, when the astronaut is on the surface of the Earth, he experiences the maximum gravitational acceleration. So here we can say that the force on the astronaut when he is on the surface of the Earth is given as mass times g. Okay, mass times g, and we know that g is usually given as 9.8, right? We know that g is usually given as what? 9.8. Forgive me. It's usually given as 9.8 meters per second squared. Okay, meters per second squared. All right. So the mass of the astronaut, which is 75, okay, forgive me. The mass of the astronaut, which is 75, times the acceleration or the gravity, which is 9.8 meters per second squared. But when you multiply this, it gives you 735. 735 newtons. 735 newtons. All right. So you realize that the closer the astronaut gets to the surface of the Earth, the greater the attractive force between the astronaut and then the surface of the Earth. Now, usually in space, astronauts feel weightlessness due to the fact that outside the surface or outside the gravitational pull or further away from the surface of the Earth, the gravitational acceleration reduces. And since there is no other force apart from the gravitational force acting on the astronaut will eventually experience weightlessness. Now, this gravitational force is what is responsible for the orbiting of the Hubble space, or for the orbiting of satellites around the Earth, okay? Because this gravitational force will in an event produce some sort of centripetal force, will be some sort of centripetal force which will cause the rotation of the satellite around the surface of the Earth. All right, around the surface of the Earth, or way above the surface of the Earth, I must say so. All right, thank you.